Oh, all right. Hello, everybody. Welcome to another lovely episode. I believe episode 11 of ChatLoopBackOff. This is a program that dives deep into the realms of the cloud native landscape, or in this case, it'll be a sub-project of Kubernetes. If we've never met before, it's my pleasure to meet you, so to speak. Thanks for joining me. I'm Jeffrey Sica, but a lot of you may know me as Jeffy, kind of that everywhere on the internet. Thrilled to have you today and join us for an episode focused on Kubernetes DRA, also known as Dynamic Resource Allocation. It is going to be an entire episode dedicated on a single Kubernetes feature, and that might seem a little weird or wild, but it should hopefully make some sense once we get into it and, talk about some topical applications for it. If you've never tuned into this live stream, welcome. This is a live stream that's kind of a sibling to a similarly named event that I run at different KubeCons called ChatLoopBackOff. That's an event where we have two community members that are pitted against each other to accomplish a technical challenge, pretty much of my choosing. And I'm kind of a sick in the head individual that likes making people suffer doing silly things with Kubernetes. In this case, this is meant to be a little bit more laid back and kind of more education oriented, but regardless, it's meant to be fun. The idea behind this one, though, is we try to pick a topic and learn it live. So with that goal in mind, I have not done much in-depth research. Most of the time, I will go into a chat loop episode having done nothing. I will glance at the docs really quick just to make sure that I can run a demo or do something like that. This one, it's part of Kubernetes, and I have probably above average knowledge, so shall we say, of Kubernetes. But also, this happens to be in a how do we put it? This is something that I have a background in as well. So this will be a little bit more. On top of that, I want to make sure that there was a way to demo DRA with kind locally, not having to spin up a bunch of crazy, clusters. So I did look a little bit more into this. Normally, we try to go in much more, zero knowledge and then learn together, but bear with me. Regardless, I haven't done the demo, so I think we're all going to walk away from something having learned a thing or two. During this live stream, please feel free to drop questions in chat. I'll get to as many as possible. Like I said, the goal here is that we learn together, so if you know the answer to something or I look like I'm stuck and you have an idea for me to follow, please speak up. Again, there's no ego here. This is all just here to mess around and learn things live. That said, this is an official live stream of the CNCF, and it is subject to the CNCF Code of Conduct. Please don't add or say anything in chat or, ask questions that might violate the Code of Conduct. Respect your fellow participants. Please respect me. Lastly, this video will be put on our YouTube channel afterwards, so if you haven't made the live stream, hopefully you're watching this on YouTube and you can learn along with us just, asynchronously. With that, also, there hasn't been very much in the way of news. I don't know if it was mentioned in the last episode, but we had 6 new CNCF projects get voted in. And let me pull those up really quick. Where are you? Right, so we had Radius, Coordinator, Kubean. I don't know how to pronounce it, but I'm pronouncing it Kubean. Kubean. Kairos, Connect, and KubeSlice. And I was talking with someone recently, and they had to ask, okay, so you had 6 new projects get added to the sandbox. How many of them start with the letter K? 4 of them. So let's just move on. Yeah, it's a problem with our community, but makes sense. All right, let me move some windows around. Let me share my screen here. Oh, what up, Taylor? Okay, entire screen, screen 1, share. Should be there. Yes. All right. So as usual, I write notes as we go. I kind of plan this and do this as we go. So all these notes will be posted in the CLBO GitHub repo. So if you're curious, that'll also all be cross-linked in the YouTube description. Make it nice and clean. All right, so first, let's talk about Kubernetes. Believe it or not, let's start with what Kubernetes is and what it does from a resource level. Then let's talk about what DRA is trying to solve, why DRA is such a big deal right now, and then we're going to do a quick, hopefully quick demo. And thankfully, the demo already exists from what I saw. And thankfully, the folks actually building out DRA within Kubernetes use this as a thing you can fork, copy, and build your own DRA drivers. So we'll get into what that is. So also, let's make that a little bigger. So Kubernetes, this is going to be boring to some, but what does Kubernetes actually do? Kubernetes takes workloads and runs them and attempts to, with a best effort, run the workloads across whatever resources you give it, whatever compute nodes that you give it. So when it was built, and I'll say a vast majority of people that use Kubernetes, they're mainly focused on, we'll say 2.5 things. They're focused on CPU usage, they're focused on memory usage, and then that half, because, you know, most don't think about it, some really need to think about it, they're thinking storage. So storage, like whether the storage is fast or slow, how much of the storage is available to the workloads, that's the main thing. But when you're talking, you know, Kubernetes in general, you're specifying your workload to fit and have limits with a certain amount of CPU and a certain amount of RAM. That works, except when you're trying to do things that involve GPUs or other expansion cards like TPUs. Most people treat TPUs and GPUs the same, but they are distinct resources, distinctly separate resources. And so Kubernetes natively does not have a really good story around that. So Kubernetes at a resource level, we're really only focused on CPU, GPU, maybe storage. Also, since Taylor, I think you are still lurking, please speak up and tell me if I am not making too much sense. I trust you to keep me in line. Also, I need to apologize to everyone ahead of time. I'm still getting over a wicked head cold, and I'm going to be clearing my throat. And it's really hard for me to mute while I'm talking, so I'm going to kind of move away from the mic to not breathe, but cough. We'll get through this. So what is DRA trying to solve? DRA is trying to make it so that you as a consumer of Kubernetes can dynamically define resources that your cluster could consume, and then provide a framework for you to specify workloads consuming, maxing out, and just allowing you to divvy up those resources in a very cloud native way. So why is DRA such a big deal right now? I mentioned GPUs and I mentioned TPUs. TPUs are TensorFlow processor units. They're just very, very good at math, just like GPUs are very good at floating point calculations. AI. Really, it comes down to being able to do floating point calculations and tensor math very fast. Kubernetes was originally built to handle things like, I want to scale up my Meta Facebook workload. I want to be able to serve my copies of Spotify, at large cloud scale. Kubernetes was never originally meant to, or didn't even really think about things like what are now more traditionally HPC style workloads. Now, that's not to say that you can't do GPU style workloads or GPU enabled workloads within Kubernetes right now. You can. Nvidia has released something called the GPU Operator, and let me also make sure that there's a link to that. So Nvidia has built out something called the GPU Operator. What the GPU Operator fundamentally does is creates a bespoke, custom, opinionated layer around workloads requesting GPU resources and making sure that those GPU resources are served to the container in a somewhat supported, generally supported, but clean way. Certainly better than if you were rolling this by hand and you don't have any expertise in passing GPU resources into a container. It's a whole thing. Bit of a tangent, but even under the hood, you are running a separate container runtime that is curated by NVIDIA to pass in these GPU resources. So it's a whole thing. It's not clean. It's not easy, right? So what DRA is proposing is a way to do that, but at an abstract level so that you don't have to roll all of your own custom tooling, and it's also tracked in a much cleaner way that is, again, Kubernetes native. Hopefully all of that made sense. It's a lot of, I don't want to say fluff, but it is also a lot of complex topics that are being meant to that we're trying to make easier to consume, so you don't need to be an expert in all of these different resources, right? Whew. Okay. I feel like that was a whole lot of talking just staring at a VS Code screen. Let's actually have a little bit of fun. So sure, that's the NVIDIA GPU Operator. This is also something I run on my home lab. This one I will actually show really quick. Oh, I made sure that kind was running all right. This is also going to look like it's horribly broken. That's on me. One of my nodes is currently, shall we say, misbehaving, and I have not had time to mess around with it. That said, when you're running the GPU operator, it's setting up the NVIDIA container toolkit. Like I said, it's kind of running its own CRI to pass resources into the container. And it's also, doing validation that the machine actually has an NVIDIA GPU. There's feature discovery, and this is kind of cool. It does a whole lot more than just NVIDIA feature discovery. It's like an expanded version of the Node feature discovery, or the Node feature exporter. And then just a bunch of other ways to export NVIDIA resources so that fundamentally you can make a request. Is it going to show up on this one? Or do I have to just go to the pod itself? Let's go to the pod itself. So you can make requests saying, hey, I want nvidia.com/GPU and I want one GPU. And then the GPU operator itself is the thing that is going, okay, I see that there are ideally 2 nodes, and based on those 2 nodes, I see there are 4 GPUs that can be allocated. This workload is going to consume one of them. So again, I wanted to kind of show the GPU operator and show how it's handling the similar concept that DRA is doing, but DRA is doing it in a very generic, again, Kubernetes native way. So Kubernetes SIGs, what was it? DRA example driver. So the folks developing DRA are wicked smart, and they have also set up an example driver. And not only have they set up this example driver that is meant to get anyone running, up and fast, they also have a quick start. It is my favorite thing, and it is the thing that I always look for, quick start or getting started section. This way we can actually try and get things running in the short amount of time that we have. So to be clear, I just kind of skimmed through this and made sure, all right, this is hopefully something that I can get working. Also, make sure that I had, crap, I didn't actually see if all the prereqs I had are installed correctly. We'll find out. But I saw that it needed kind and called it good enough. So here we go. So first off, it wants us to clone things and cd into the demo. Code, CNCF CLPO, ChatLoopBackOff 5, cool. So we are in the demo. From here, we will build the image for the examples resource driver. Is it really as simple as just these scripts? I like that. So demo, build driver. So it's going to run so it's going to reference this common.sh, which looks like it's setting a bunch of default variables. Yes, I will run through bash scripts before I just run them. I typically try not to YOLO everything. And then it's running build driver image. Current dir common. Make Docker generate, and then it's making something in deployments, container makefile. Okay, so this just looks like it's trying to build a specific container image. That seems clean. Clean enough. Now let's see if I run into any random issues like Jeremy or I have both had. And away it goes. I guess while that is building, I can point out that I am running an instance of Ollama kind of on my home lab, just because, I don't know, this is my kind of fun little hobby. It's the way that I try and stay current on stuff. I have 2 Ollama instances. One is running Llama 7B, and the other was running, I actually don't remember. I think it was Mistral 7B. It's on super old hardware, though, so it's not exactly performant, but the kind of jobs that I'm messing around with are meant to be more kind of scheduled cron jobs, and they don't have, they're not like you're interacting with it directly, so if it is getting like 10 tokens a second, or even like 2 tokens a second, it's perfectly fine. Just wanted to call that out and say something while we're watching the paint dry or the container image build. Anyone that may actually be watching and listening, I'd be curious how many are using or have had to use GPUs in their workloads, either for fun or as part of, $ day job. I'd also be curious if anyone's actually already messing with DRA. So one thing, hey, it's done. One thing to note, currently DRA is an alpha feature of Kubernetes. So it requires you having to enable it. It does not immediately enabled out of the box. All right, so wrong window. So we built the driver, and now we just have to create a cluster. I am curious, like I said, if this will also automatically enable the alpha feature, if that's a separate step. And my question is answered. So create kind cluster will create a kind cluster with, a name that it's going to specify an image, but then the cluster path, which will load this up. And then runtime config resources. So it enables that resource endpoint or that API, I guess. Cool. That makes sense. Interesting. So it is still pinned to 128.0. So 130 was just released. I'm curious if DRA made it into beta then. Let's check the release notes while that kicks up. Actually, what am I doing? The doc itself would say whether it is alpha or not. Okay, so it is still feature state alpha, even if we were using 1.30. Hold up, before you begin, Kubernetes 1.30 includes cluster level API support for DRA, but it still needs to be enabled explicitly. Okay. So even if we had gone, or even if we bump this, we're still going to need to enable it. So nothing functionally changes. So just make sure we're on the right cluster now. We're not on my home lab. We can connect to it and see all the lovely namespaces. Let's get back to following the documentation. CordionS at CD kindnet. CordionS at CD kindnet. Okay. So now we need to use Helm, and Helm is going to install this resource driver. So from the look of this, it's going to create a namespace called DRA example driver, and then it's going to spin up a deployment. And also looks like it has a plugin that runs alongside the kubelet. Keep picking the wrong windows. And those are running tight. So we can show the initial state of available GPU devices on the worker node. Product name, latest GPU model. That's unlikely. All right, so next we deploy 4 example apps that will have resource claims and different parameters. Now this I'm kind of curious about. We're hitting the point where I have not actually, like, I know DRA in concept, I know their approach. I haven't actually seen what the YAML looks like, and YAML makes the world go round, or so I've been told. So this is going to shrink this a little bit. Okay, so oh, hey, just scroll down a little further. All right, so GPU test 1 says we have 2 pods, 1 container in each, 1 GPU in each. Then we'll have 2 2 containers in a single pod that share GPU. 2 pods, 1 container each, 1 GPU. 1 pod, 1 container claims 4 GPUs. This is good. This supports all of the, all of the different possible ways that you could want to slice up a workload and a resource. Let's see how it does it. So it creates a new namespace, GPU test 1. This is one of the new kinds, or I guess one of the new APIs or YAML files, whatever you want to call them. So resource.k8s.io, it's in alpha 2, resource claim template. So in the namespace, we're saying gpuexample.com, and we're saying the resource class name is gpuexample.com. Pod 1, normal pod spec with a resource claim. So we're saying resource claim, directly use that template name. Okay, so there are 2 different pods with the same resource claim template name. Excuse me. And then let me just double click this and keep it open. Right, so this looks like it's assuming there are 2 different... Wow, brain fog. Or just I'm slow right now. So by defining this resource claim template, we're saying this resource class, gpuexample.com, and the pod templates themselves will just one-to-one these resources. Seems cool. So, oh wow, we just spin all of them up at once. Okay. So there's the resource claim template created, then the 2 pods. So let's see what where are you at? GPU test 2 comes up as, or looks like. So similar thing, resource class name, GPU example. Which one did this look like? Okay, so this is 1 pod, 2 containers, shared GPU. So this and this essentially are the same. It's just this pod has multiple containers. Oh, that's GPU test 1, sorry. Oh. Okay. So you can, per container in a pod, specify the resources, which, now that I say that out loud, makes perfect sense. I just wasn't getting that. And so we could actually do something like this. Remove this resource claim, and then container 2 here would not have any access to that GPU, but the other 2 would. That makes sense. I'm just slow. What's resource CRD consumer? Where are you seeing that? And I will try and explain it. I am more than likely going a little fast. Yeah. Elaborate and I'll try and answer. But we have set or created all three of these example pods. So GPU test 3 looks like it shares a GPU. So without looking at the YAML, I'm going to assume it is going to look similar to how we're defining it over here with a shared resource. This is going to be very interesting. Let me just undo all that. So similar to what we're doing, we're setting resource claim, new namespace, new shared GPU, resource class name is the same. In this case, just resource claim name is the same. That rhymed. Huh. So what does GPU test 4 look like? Okay. So we're setting parameters. Oh, that's cool. And we're saying there's a spec of 4. So we're defining there are 4 GPUs. We are defining that you can reference the GPU claim parameters when you were creating your resource claim. Yep, name of multiple GPUs. We're referencing this. And then we say resource claim, name of GPUs, and then source resource claim, template name of multiple GPUs. This is a lot more abstract than I was expecting. I was expecting a bit more of a framework to divvy things up, but even that seems to be left up to the driver, which I kind of makes sense to me. So let's... Oh, one thing I forgot to do was to call pods A. We can see that in all of the GPU tests that we spun up, they are all running and healthy. So they actually spun up, did their thing. So let's look at some of the APIs that they are referencing and try and shed some light onto some of my questions. Oh, actually, before we do that, let's see if there's any other things that we need to do in this demo. I'm going to... No, we'll do it. I was going to say, I'm going to trust the demo to have done what we expected. So this is going to dump logs from each app and verify GPUs are allocated to them. Seems okay. And of course, these GPUs are just, fake. But still, it shows that it's trying to do what it would if this was like an Nvidia GPU or an AMD GPU. In the example, no actual GPUs are made available. That is correct. But each one is given an environment variable that kind of defines they got what they were expecting. And now if we look at the claim allocations, we should see that everything is back to normal, meaning they are available to be allocated. Node allocation state. The fake GPUs are indeed available. Or not allocated. Okay, so there we hit a bunch of different custom resources. I want to see what's actually kind of being defined here. Like resource claim. What is this resource claim template? I assume this is just a CRD that is being built as part of the example driver that we built. Because, again, example.com. So let's try and put this together through the docs. So resource class, what resource driver is handling a certain kind of resource. Presumably, that would be gpu.example.com. Resource claim is defining our particular resource instance. I'm just reading text, but that's how we actually claim the resources that we define. This is very similar to how we handle volumes in Kubernetes. Like there's persistent volume, there's a persistent volume claim, one-to-one. Or at times there can be multiple claims to a single PV. Wait, can there be? Oh my God, I just broke my brain for a second. Because like I know for we're gonna tangent a second so I actually say the right thing. I know that you can have read write many, which means there can be multiple instances of or different pods referencing the same PVC. But there's a one-to-one relationship of a PV to a PVC. Yes. Worked through that. Sorry. Pod scheduling context used internally. So this is never exposed to a user. Resource slice. Was that referenced here? I don't think we used a resource slice in this demo. But we did, every time I pop back here, it's like scrolling all the way to the top. We did hit on resource claim parameters. Because here's I think it was on GPU 4. Yep. So GPU claim parameters, but in this case, this is an extension of a resource claim parameter, I imagine. There it went again. Parameters for resource class and resource claim are stored in a separate object, and it is around the resource driver that we install. The developer of the resource driver decides whether they want to handle these parameters or not. Oh, hey, their example involves cats. I'm here for this. So you define your resource class, and then you define your resource driver. So But we do have one of these, right? Yeah, DRA example driver. Let make sure I didn't fudge that. Okay, so there's really only 3 CRDs installed right now: device class parameters, the GPU claim parameters, and then the actual node allocation state as part of resource.example.com, which is our fake DRA driver. Pod spec, resource claims. So this is an example of them defining a cat that can be claimed that has a color of black and a size of large, and saying they have 2 containers in their pod. And they want cat 0, which follows the large black cat claim template. Wow, that was a mouthful. And then the second container requests a separate resource different from the first, but it is still following this claim template. This is I think the thing that I really want to read out loud. So like I mentioned much earlier, well, in the beginning, Kubernetes really focuses on CPU, RAM, and to an extent, storage. But in contrast to those, and extended resources managed by device plugins and advertised by Kubelet, Scheduler has no knowledge of what dynamic resources are available in a cluster or how they should be split up to satisfy the requirements. So resource drivers are the ones responsible for that. They mark resources as allocated once, and then they will free them up when resources get deleted automatically. But that's scheduling without structured parameters. Ooh, this is important for people in very large or high-performing clusters. Scheduling pods, which use resource claims, is going to be slower because of the additional communication required. Because remember, when you are scheduling something, you are going to be scheduling something, and it is going to have to hit multiple things, not just the scheduler, not just the kubelets of the nodes. It's also now hitting a completely separate thing, which is the resource driver. And that resource driver, it's funny to call it a driver, but ultimately all that is doing is it's a controller. And so it is tracking the state of the cluster, tracking what resources have been used or not used that it's paying attention to. In the case of the demo, it's, those fake GPUs. And then it is telling the scheduler what can and can't be scheduled, right? So scheduling can be delayed because of that added layer of communication. If they're unstructured resources. When a driver uses structured parameters, the scheduler can take responsibility and doesn't have to hit that controller. Monitoring resources around this. Kubelet provides gRPC service. That's pretty much normal. And then here's essentially how to enable DRA. Okay. So what all have we actually done right now? Build the driver controller image, run through. Oh, demo with DRA. I should add that link there. So we built the driver controller image. We ran through the demo where we also took a look. YAML files. And then we did a very brief DRA doc walkthrough. It is... It's interesting. Like, trying to figure out what I want to say. So DRA does exactly what I thought it did before this deep dive. But I had honestly thought, and this isn't really a knock to anybody, I had thought it was a little more structured or a little more opinionated. But that said, I understand why it's not. The more opinionated something in Kubernetes is, the less, in my opinion, the less adoption there will be. Like, we want people to try and standardize on this is the way to define resources. So rather than Nvidia rolling their own GPU operator, they can hopefully build something a little bit more Kubernetes native that doesn't require 50 different pods. Not 50, but still, on my meager home lab, it's what, 15 or 16? Just to be able to allocate a GPU and have it be consumed by a container. But on top of that, this doesn't have to be for GPUs or for TPUs or anything like that. It could be for arbitrary resources. Here's a crazy thought. And this kind of goes to a silly idea that Bob and I had ages ago around coffee netties. Wouldn't it be funny, a Keurig makes a cup of coffee based on a pod. What if we, had kubelet running on a Keurig, and then you could schedule a pod that would create a cup of coffee? As we are seeing the Kubernetes API get used in weirder and weirder ways, creating a framework to define arbitrary resources, not even compute resources, makes more sense. I'm actually convincing myself as I talk it out loud. It makes more sense for this to be, again, as not opinionated as possible. And when it comes to creating resources that do not have structured parameters, sure, it may be slower because there has to be additional communication with that controller, but that might also be beneficial. That might be a way for that resource driver to do a check and make sure that there's some external thing that is, not tracked by Kubernetes and is good to be released or good to be consumed or acquire a lock on it. So, yeah, DRA is still very, not vague, but open-ended. But I think within the next 2 years, we're going to be talking about it even more than we are now, because I think there are going to be quite a number of different companies and products that are using, dynamic resources. And I think that's where I'm going to leave it. Thank you to everyone that listened. Hopefully this was not too abstract. Normally with some of our other projects, it's kind of, let's, take something off the shelf, mess with it, essentially put an input in, see what the output is, and then let's talk about how it can be used. But DRA is a lot more open-ended, and DRA is going to, I think, be a bigger deal than even, KubeCon in Paris made it out to be. So again, thanks everyone. I will not be the one hosting next week. I believe next week is Mafi. Let me double check quick. Oh no, next week is Jeremy doing Kyverno round 2. So Jeremy and I had talked, and there was so much in Kyverno that it warranted a second round. So those of you that were around for round 1, get ready for a whole second episode. For those that weren't, please go look at the first episode of Jeremy digging into Kyverno. I'll be sure to link it in the notes for this episode as well. So cool. Thank everyone, and I hope you have a wonderful and hopefully more dry Thursday than I am right now. That said, we've been in a drought for the last 2 years. I am perfectly happy to have it rain for like 2 weeks nonstop, but there you go. All right.